In this session, we're going to look at dependent and inconsistent systems. And while the work that we're going to do in this section is going to be based in 3x3 systems, what I want to do is start off with looking at stuff in two variables. If we consider y is equal to 3x plus 2, then from an ordered pair perspective, we could put values in for x, say 0, 1, and 2, get values out for y, say 2, 5, and 7, and then plot those points in the xy plane, and what we would end up with is points that line up and in fact make a line. Now the deal is there are an infinite number of solutions to the equation y equals 3x plus 2. In fact, every single point on the line is a solution to that equation. You see, because a solution is a value or values that we can put into an equation and make it a true statement. So the reason that this equation has an infinitude of solutions is essentially that we have more variables than we do equations. In the case of a 2x2 system, what we have is two lines that more often than not intersect in the plane, and that point of intersection, xy, is the single solitary point that exists on both lines, that is, that satisfies both original equations. This is not the picture of a dependent or an inconsistent system. This is your run-of-the-mill, I have a solution system. In the case of the 2x2 system, an inconsistent system would be one where the two lines share no points in common, which would mean they have no points of intersection, which would mean that they are parallel lines. And you could see that, say if I have y equals mx plus b, say that's one of my equations, and another one is also y equals mx plus b, I would be able to see that this is an inconsistent system, right? One that has no solution, by simply examining the slopes and observing that they had, say, a different y-intercept. In the case of a dependent 2x2 system, what we have is two lines, well, seemingly two lines, but when you graph them, they would be on top of each other, right? So you can either have no point of intersection or infinitely many points of intersection, and that would be the inconsistent or the dependent system, respectively. This you should know based on previous knowledge. Now, when we go to the 3x3 case, where we're dealing with planes, we could have planes interacting in such a way that they don't share a point in common. So this is one way we could have an inconsistent system. Having three parallel planes, one on top of another, would also give an inconsistent system. In fact, any way that you get three planes together in such a way that they do not share a point, you'll have an inconsistent system. And those systems are relatively easy to deal with because you look for a contradiction while you're solving and you say no solution. However, we could have planes that intersect along more than one point, and in this case we have planes intersecting along a line. Or we could have three planes coincident, right? Kind of like the two lines on top of each other. In which case, our solution is a little bit more difficult to write. It's easy to recognize when this happens, but it's a little more difficult to write. And that's going to be a lot of the focus of this particular video. Only a few examples, but let's jump to them. Give the complete solution to the system of equations. Our system is 2x minus 3y minus z equals 0, negative x plus 2y plus z equals 5, 3x minus 4y minus z equals 1. As before, I'm going to number these equations, 1, 2, and 3. And then kind of looking holistically, like bird's eye view, is what we have. I could eliminate the x's. I'd have to multiply to do so. Likewise, the y's. The z's look like they're ready to go. So we're going to take equation 1 and add to it equation 2. And when we do that, we get equation 4, which is x minus y equals 5. Why don't you go ahead and grab equations 2 and 3 and add them together, pause it, and come back. I get 2x minus 2y equals 6, which I'm going to divide both sides of by 2 and get x minus y is equal to 3. Call that equation 5. Now, putting equation 4 with equation 5, I see that they're x minus y equals 5 and x minus y equals 3. If you really wanted to, you could multiply, say, equation 5 by negative 1 on both sides, and then, add that to equation 4, and what you'd end up with is 0 equals 2. No, it's not. Sorry, that's a reflex. Folks, this is a contradiction. Whenever you're trying to solve an equation or a system of equations, you get a contradiction. It's got no solution, which I'm going to indicate using the empty set, that zero-looking thing with a slash through it. What it's saying is the set of solutions is empty, the empty set. Next, we're asked to give the complete solution to the system of equations, and our system is x minus y plus 5z equals negative 2, 2x plus y plus 4z equals 2, 2x plus 4y minus 2z is equal to 8. Not necessary for our process, but I'm noticing that all of the numbers in the third equation are even, so I'm just going to go ahead and cut those down to size. You can do that at any time when you're solving a system of equations. Let me rewrite this system. Okay, so my new equation 3 is x plus 2y minus z is equal to 4. And now why don't you go ahead and do what you need to do with equations 1 and 2, and let's get rid of, let's say the y's. And then take equations, let's say 1 and 3, and do what you need to those to get rid of the y's again. Go ahead and pause the video, quick like a bunny, and come back. Okay, so what I did is added equation 1 to 2 and got 3x plus 9z equals 0. Then I multiplied 2 times equation 1 and added that to 3, and I got, lo and behold, 3x plus 9z equals 0. I've got the same equation twice. That's indicative of a dependent system. If you really wanted to, you could take, let's number that equation 4 and equation 5, although they're the same. And we could say, take equation 4, subtract equation 5. And if I did that, it would be 0 equals 0 as a result. And it's an identity. And as soon as I see an identity, I know I have something that's dependent. So now what I need to do, and this is where it gets a little bit difficult, but I think we can work our way through it. What I want to do is I want to take either equation 4 or 5. I mean, they're the same one, so it doesn't matter. And I want to solve for the variable that's easiest to solve for. Sometimes it'll suck no matter what. Looks to me, though, like I can solve for x and get x is equal to negative 3z. It's very important to note what we have right now. What we have is x in terms of z. In other words, what I have is x equals something with z. Okay? Now, what I want is I want something else in terms of z. I already have x in terms of z, so what do you think that something else is? That's right. We want y in terms of that same variable. So what we're going to do is we're actually going to take x equals negative 3z, because, it does, and put it into either equation 1, 2, or 3. And looking them over, I'm thinking I'd like to put that into equation 1. Let me rewrite equation 1. Remember, it was x minus y plus 5z equals negative 2. And we're going to substitute x is negative 3z. So negative 3z in place of x. The rest of it comes along for the ride. Minus y plus 5z is equal to negative 2. And you notice now we have an equation that has only y and z in it. We want y in terms of z. In other words, what we want is y equals something with z. In other words, solve for y. Go ahead and do that, see what you get. And I get y equals 2z plus 2. So now I have an expression for x that depends on z. I have an expression for y that depends on z. And so for any particular value of z, we have x and y. I won't show you the details, but these make a line. The way we're going to write our answers, well, there's two different ways depending on, I don't know, whichever you want. There's one that I think is easier, one that I think is a little bit trickier to understand. What we're looking at is the set of ordered triples, x, y, z, such that, and then what you want to do is you want to tell me what they are. What's x? Well, x is negative 3z. What's y? Well, y is 2z plus 2, right? Those expressions for z. What about z? What is z? Well, check it out. Z can be any real number, right? So I'm using a symbol that says z is in the set of real numbers. And this is actually a perfectly valid way to write it down. You see, you're telling me what x is. It depends on z. You're telling me what y is. It depends on z. And you're telling me about z. It's any real number. That works. Sometimes, though, we might want to say that x, y, z is equal to an ordered triple. Well, here's the deal. I don't get to say negative 3z, 2z plus 2, and z, because you can't say that z is z. People will go, well, duh. So let me clear that out. So if I can't say z is z, what can I say z is? Like anything else. A lot of times you'll see a t, and that's called a parameter. And if z is t, then x would be negative 3t. You see, it still depends on that third coordinate. If z is t, then y is 2t plus 2. And this is a way to give my answer as an ordered triple. So we have set notation, and we have an ordered triple. And I would, in fact, accept either of these as an answer. In my experience, people generally go for the set notation. Next, same instructions, give the complete solution. X plus 2y plus z equals 4, and 2x minus y minus z equals 3. By the way, you see that word complete? That means saying it's dependent isn't good enough. You got to tell me what the solutions are. Wait a minute, there were only 2 equations. That's right, and 3 variables. Remember what happened when we had 1 equation and 2 variables? If ever you have more variables than equations, you have a dependent system every single time. So what we want to do is we want to still eliminate a variable. I'm going to add these 2 straight away, and we're going to get rid of the z's. So when I add these, I get 3x plus y equals 7. Guess what I'm going to do? Solve for y. So I get y equals negative 3x plus 7. Now, what I have is y in terms of x. Since I have y in terms of x, I want something else in terms of x now. What do you think that something else is? That's right, z. So what I'm going to do is I'm going to put, let's see, y equals negative 3x plus 7. I'm going to put that in place of y, I don't know, eeny, meeny, miny, in the second equation. It's just a matter, I just felt like it this time. So I have 2x minus the quantity of negative 3x plus 7 minus z is equal to 3. When I distribute the negative and then solve for z, because remember we want z in terms of x, I get z equals 5x minus 10, which you should verify. Now, since I have stuff in terms of x, when I write my set notation, the set of x, y, z, such that I'm going to say that x is the one that's any real number. There, my pen's squeaking. And then we're going to say that y is negative 3x plus 7, and then z is 5x minus 10. Close it up. There we go. If you wanted to parameterize it, you would say that the ordered triple x, y, z is equal to t, comma, negative 3t plus 7, comma, 5t minus 10. Right, so I would take either of these. Now, what does it mean that the solution looks like this? Well, that it's dependent. Now, how would you check it? Let's go there with it. How would you check it? Well, x is any real number, so you're gonna just leave x as is, as a matter of fact. Y has an expression, negative 3x plus 7, and so you would put that in place of y into both equations, right? You one at a time, but both equations. And then z is 5x minus 10, so you'd put 5x minus 10 in place of z. And then you would simplify stuff and make sure that you end up with a true statement there. One question that comes up in these things is, I solved for y in terms of x, and then I got z in terms of x. What if I had solved for x in terms of y, and then I got z in terms of y? That's fine, I don't care, it doesn't matter to me. You would have to say that y is any real number, and then your other expressions would depend on y, right? They would include y there. When I'm grading a test, I don't see if you did it the same way I did. I see if what you did is correct. For our last example, and this will go fairly quickly, give the complete solution. System is 2x minus 6y plus 4z equals 8, 3x minus 9y plus 6z equals 12, 5x minus 15y plus 10z equals 20. Folks, I notice in the first equation all of the numbers are even. In the second equation all of the numbers are divisible by 3. In the third equation all of the numbers are divisible by 5. So I'm going to take the first equation, divide it by 2, the second equation, divide it by 3, the third equation, divide it by 5. Why don't you do the same? Pause the video. We'll come back. Break! I'm seeing in triple. I got the same equation 3 times. It's x minus 3y plus 2z equals 4. Guess what that means? It was all one plane to begin with. So what we want to say is that it's the set of ordered triples x, y, z such that they're on the plane. Well, how do you write that down? You write down the equation of the plane. So the set of ordered triples x, y, z such that x minus 3y plus 2z is equal to 4. In case you're wondering, I picked the equation that I did just because there are smaller numbers. We could have used any of the original equations of the plane. Here in the answer, they are the same plane after all.